Welcome to V.O.C.C. Watch, YouTube channel of V.O.Chidambaram College, Thuthukudi. I am Dr. D. Princess Jeba, Assistant Professor of Chemistry, V.O.Chidambaram College, Thuthukudi. Today we are going to discuss about phase rule. Phase rule is an important tool which is used for quantitative treatment of systems in equilibrium. It enables us to predict conditions that must be specified for a system to exhibit in equilibrium. So first of all, we must know what is known as a system which is in equilibrium. Equilibrium is nothing but if two or more phases, or if a system exists in more than one phase. What is known as a phase? If a system is in both solid as well as in the liquid state, for example water as well as ice. If both of them are in equilibrium, equilibrium means both of them have the same composition in the first as well as the second phase. This phase rule enables us to predict at which condition both the phases tends to exhibit in equilibrium. So this is the importance of phase rule. This phase rule was first enunciated or coined by Willard Gibbs. So it is otherwise called as Gibbs phase rule. Phase rule is applicable for the systems in heterogeneous system. What is known as a heterogeneous system means if all the components are in a single phase, it is called as a homogeneous system. If all are liquid, then it is called as a homogeneous system. Whereas if a solid, liquid as well as gaseous state all exhibit in equilibrium, then it is called as a heterogeneous system. This rule predicts qualitatively the effect of temperature, pressure and concentration for the system which is in heterogeneous equilibrium. What is known as a qualitative prediction means it won't give a specific value of temperature or pressure, but it gives a qualitative determination of temperature and pressure as well as the composition which is required for the system to exist in equilibrium. So what is Gibbs phase rule means? If in a heterogeneous system in equilibrium which is not affected by gravity, electricity and magnetic forces, the number of degrees of freedom is related to the number of components, number of phases existing at equilibrium. So mathematically it is expressed as F is equal to C minus P plus 2. Degree F is nothing but it is called as the degree of freedom. C is the number of components, P is number of phases and the 2 is nothing but it is additional variables of temperature and pressure. So in order to know the Gibbs phase rule, we have a clear-cut idea about C, P and F. C is component, P is phase and F is degree of freedom. So first we have to discuss about phase. Phase is defined as physically distinct, homogeneous and mechanically separable part of a system. If you consider a thermodynamic system, if you have two phases, that is if you take water molecule, it exists in ice as well as in water. So both are physically distinct. Ice is a solid whereas a liquid water is a liquid. So mechanically by hand picking we are able to remove ice from water. So this is called as a phase. That is physically it is distinct from the other system, other component, and it is homogeneous and it is mechanically separable part of the system. For example, if we have a mixture of gases, all the gases are completely miscible. For example, hydrogen, oxygen, chlorine, both are completely miscible. Then all the gases, we call it as air, and air is considered to be in one phase because we are not able to separate a gas from another gas since they are completely miscible. Similarly, if two liquids which are completely miscible with one another, then these two liquids are considered to be in a single phase. Both of them are in the liquid and it is considered to be a single liquid. Whereas a system, if it has two phases, for example, as I said earlier, water in the liquid state as well as water in the gaseous state. So liquid is entirely different from gas. We are able to separate as we change the temperature. So next one is component. So that the C in this phase rule equation. So component is nothing but minimum number of independent variable constituents which are required to express the composition of each phase in the system. If a system consists of various phases, so what are the minimum number of independent variables which we can require to express the composition of each phase. For example, the same thing, water and ice. If you want to determine the composition of ice at a particular temperature and composition of liquid water at a particular temperature, we need H2O or water or a single component. We need the volume of water, or we have a minimum number of independent, so it is independent, and component is nothing but the number of minimum number of like water independent variables which we require to express the composition of each phase in the system. So in a chemically reactive system, if for example in a chemical reaction there are various reactants which will give some amount of products. In explaining the particular chemical reaction, the number of components may vary, and the formula is C is equal to N minus E. C is the number of component, N number of chemical species, E is the number of independent equations relating to the concentration of the species. Each independent equilibrium involving the constituent count as one equation. So from various example we are able to specify this equation. So the condition that if the solution is electrically neutral, for example, if we have the same number of positive as well as the negative ions which is present in the solution, then it is considered to be the one equation which specifies the ions are required to give the number of components, For example for the number of components is, for example, if you take a sulfur system, we have sulfur is a single component having a chemical formula S, whereas sulfur exists in 4 forms. One is monoclinic sulfur, which is in the solid state, rhombic sulfur, which is also in the solid phase, liquid sulfur, which is in the liquid phase, whereas sulfur vapor, which is in the vapor phase. But in monoclinic form or in the rhombic form, both are physically distinct forms, because monoclinic is a different crystal structure, whereas rhombic is a different crystal structure. We are able to distinct it physically by seeing the 2 types of sulfurs. Liquid sulfur entirely in the liquid form, whereas vapor sulfur is in the vapor form. So from this, what is the number of components? Component is 1, that is a chemical species. Component is a distinct chemical species. Here the chemical formula for sulfur in monoclinic, rhombic, liquid and vapor, whatever it may be, it is sulfur. So number of component is equal to 1, whereas the number of phases is 4, because monoclinic sulfur exists in monoclinic crystal lattice, whereas rhombic sulfur exists in a rhombic form, liquid sulfur exists in liquid phase, whereas vapor sulfur exists in vapor phase. Similarly, if you take water system, we have water molecule H2O, chemically distinct H2O. So component is 1. The same component exhibits as ice in the solid form, liquid water in the liquid form and water vapor in the vapor form. So number of component is 1, whereas number of phases is equal to 3. Whereas if you go for salt plus water system, certain salts are capable of existing as hydrates with different number of water molecules of crystallization. Sodium sulfate 7H2O, sodium sulfate 5H2O, and sodium sulfate, if it exists in different types of hydrates, but then each hydrate corresponds to a particular component. Each hydrate corresponds to a particular component, because in each hydrate the number of water molecules differ. So both of them exist as a different component, whereas the number of phase is equal to 1, because the compound is in the solid phase. So this is the definition and example for number of components. Similarly, next one is F, or degrees of freedom, which is represented as F in the phase rule. It is defined as minimum number of independent variables such as temperature, pressure and concentration, which can be specified in order to define the system completely. So if you want to define the system or define the existence of various phases in the system, we require some variables, that is temperature. For example, at 0 degrees Celsius ice alone exists, or ice is in equilibrium with water, whereas at 100 degrees Celsius, water which is in equilibrium with vapor. So temperature is a variable which gives an idea or which gives a complete definition about the number of phases by which a component exists in equilibrium. So degrees of freedom is nothing but minimum number of variables. So either if you need only temperature to explain this, so temperature is the variable, whereas if you need temperature and pressure, so we need various variables to explain the system. But degrees of freedom is the minimum number of variable which explains the number of phases of a system completely. For example, if a state of a pure gas can be given by both temperature or pressure and temperature and volume. So if you know at a particular pressure and temperature, the pure gas can coexist. The same example I have already quoted is water molecule in the liquid and gaseous state. We need for a pure gas, the degree of freedom is equal to 2 because we need pressure and temperature. Whereas for liquid and gas which is in equilibrium, we need any one variable, either pressure or temperature. So F is equal to 1. For example, if you have a mixture of gases, for example, nitrogen and oxygen, if you want to completely define nitrogen and oxygen, we need 3 variables. What is the concentration of nitrogen? At which temperature nitrogen is in the gaseous phase, and at which pressure it liquefies. So we need 3 variables for explaining the mixture of gases. What are the advantages of phase rule? So what is the need of phase rule in explaining the equilibrium of the system? So it provides a simple method of classifying the equilibrium states. By using phase rule only, we are able to explain the equilibrium states of various components. Similarly, it confirms the different systems having the same number of degree of freedom behave in the same manner. So, for example, this phase rule gives a very good idea that if the degree of freedom F is equal to 2 for 2 different systems, these 2 different systems behave in the similar manner. So it is given by Gibbs phase rule, and this phase rule is applicable to macroscopic system, that is for 1 liter or macroscopic quantities we have to apply this phase rule, and not for a single molecule we won't use. And next one is it predicts the behavior of system which changes in variables that govern the system in equilibrium. In equilibrium, when there is a rise in temperature, what happens to the number of phases? When there is a decrease in pressure, what happens to the number of phases or equilibrium of the system? Either it shifts towards the right or left, or the phases may coexist. All the other informations we get from this phase rule. Similarly, phase rule predicts that all the system, that is if there is interconversion or elimination, or the system which consists of various components all remains in equilibrium. All of them remains in equilibrium. Next one is variables such as temperature, pressure and components may be taken into account in Gibbs phase rule. And in Gibbs phase rule, we have to take into account of temperature, pressure and composition, and we won't take in the account of gravitational and magnetic forces which act on the system. The next one is application of Gibbs phase rule. So how Gibbs phase rule is applicable in order to predict the components, phases of various systems. Phase diagrams. So this Gibbs phase rule is applicable to explain the number of phases and components of a particular system by means of a particular diagram which is called as a phase diagram. From the phase diagram, we are able to calculate the number of degrees of freedom. So all the components of a system can be completely described by a graphical way. So for example, we have to take water system. So water system consists of a single component, single chemical species H2O, which is water. Whereas this species may exist in 3 forms. One is ice, water and vapor. So how many phases are in equilibrium? Solid is in equilibrium with liquid, solid ice which is in equilibrium with liquid, liquid water which is in equilibrium with vapor, and solid ice in equilibrium with vapor, At a particular temperature, both solid, liquid and vapor exist in equilibrium. So this is the phase diagram of water system. That is, when you plot temperature versus pressure at a particular composition, we get a curve like this. Here in this curve, O is the triple point and OB, this O here, this curve OB, which is called as the sublimation curve. Sublimation means conversion of solid directly to the vapor phase is called as sublimation. If a solid is directly converted to vapor, it is called sublimation. So ice which is in equilibrium with water vapor, ice in equilibrium with vapor is called as the sublimation curve. And next one is vapor pressure curve. This vapor pressure curve is OA. In OA, two phases are in equilibrium. One is liquid water and another one is vapor, water vapor. So this OA extends to a particular temperature. So temperature scale, here the sublimation curve extends up to 0.0098 degrees Celsius, whereas vapor pressure curve extend to a particular temperature 374 degrees Celsius, which is called as the critical temperature. Above this critical temperature, no liquid water can coexist. So at before critical temperature, we have two phases. One is liquid water and vapor, whereas above this critical temperature, only vapor phase coexist. So along the curve OA, we have two phases, and at a particular temperature 100 degrees Celsius, the vapor pressure of water equals the atmospheric pressure. So at this, water starts boiling. So the temperature at which the vapor pressure is equal to atmospheric pressure is called boiling point of a particular component. Here from this phase diagram, we can fix the boiling point as 100 degrees Celsius, where after 100 degrees Celsius, water starts boiled and it is in equilibrium with vapor. Then again another line which is OC, which is called as the fusion curve. Here along the curve OC, solid ice in equilibrium with water. Ice fuses to form water. So we have two phases. One is solid ice, another one is liquid water. There is a significance. This curve slant towards the lower temperature side. As the pressure increases, the curve slants towards the lower side. So there is a significance, because at very high temperature, as the temperature increases, as the pressure at very high pressure, so as the pressure increases, at very low, the temperature decreases for the fusion. So at 0 degrees Celsius, water is converted to ice. Whereas when we increase the pressure, so at minus degree, then the water becomes ice. Water becomes ice. There is again a decrease in temperature. As the pressure increases, the temperature decreases for the formation of ice. So this is evident that the volume of liquid water is very high compared to that of the volume of ice, which has a very lower volume. So next one is one dotted curve OA prime. This OA prime is called as the metastable curve. That is, it is called as supercooled water curve. That is, when we decrease the temperature and we in a very slower way, if you cool the water, that is around after 0 degrees Celsius also, there is no formation of ice, but water exists in a supercooled state, and this equilibrium is called as metastable equilibrium. That is, when a disturbance is created, suddenly it solidifies into ice. So from the phase diagram of water system, we are able to clearly explain the various phases which are in equilibrium. So along the curves, we have two phases, and a very important point called as triple point O. At this triple point, the solid phase, liquid phase and vapor phase are in equilibrium, and the temperature is 0.0098 degrees Celsius and the pressure is 4.58 millimeter of mercury. So phase rule is applicable to clearly explain the number of phases in equilibrium in water system. So we have three stable curves, OB, OA and OC, one metastable curve OA prime, and three areas AOB, COB and AOC, and one point O. So along all these curves, maybe curve OB or curve OA or curve OC or curve OB, we have two phases. If it is the freezing point curve, then you have two phases, solid and liquid. If it is the boiling point, you have two phases, liquid and vapor. If it is sublimation curve, you have two phases, solid and vapor. So, along the curves, P is equal to 2. So, from phase rule, F is equal to C minus P plus 1. So, when you apply in this, component is 1, phase is equal to 2 plus 2. So, minus 2 plus 2 get cancelled and F is equal to 1. So, along the curves, only 1 degree of freedom. Degree of freedom means either temperature or pressure may be used to explain the system. Whereas, along the areas, we have only one phase. Along the area AOC or along the area along the area BOC, AOC and AOB. Both these three areas along BOC only ice coexist. There is no water or vapor. Whereas AOC only water exists. Whereas AOB only vapor exists. So you have only one phase. So from the phase rule, F is equal to component is 1 minus phase is also 1. So 1 cancel plus 2. So F is equal to 2. You need two variables to explain the area. Similarly, at triple point O, we have three phases, ice, water and vapor. Both of them coexist in equilibrium. So you don't need any variable. This point is called as non-variant or invariant point. Only one set of variables, pressure and temperature, at which all the three phases can coexist. So any variable changes, there is a change in number of phases. Thank you.